Hi guys, Audrey here. Okay, so we know what a power series is. A power series is a series that is kind of like an infinite polynomial. So in other words, is a series that contains x's, not just known numerical values. So is a series of the form n equals 0 to infinity a sub n times x minus c to the power of n, where c is the center of that power series. Okay, so we know what a power series is. We understand when power series converge. So we've learned how to calculate the interval of convergence for a power series, which is also the domain of the power series, the x values for which the power series converges. Now the question we want to answer is, when a power series converges, to which function does it converge? That's actually oftentimes a really difficult question to answer. So we're going to approach it sort of backwards. We're going to say, if I have this function, how can I write a power series to represent this function? So this is what's called Taylor's theorem. So Taylor's theorem tells me that if some function, f of x, has a power series representation at some center C, at some center C, then that function can be written as the power series n equals 0 to infinity, the nth derivative evaluated at C, all divided by n factorial, times x minus c to the power of n. In other words, our coefficients of the power series, that a sub n, can be written as the nth derivative evaluated at c divided by n factorial. So in other words, we are saying that our a sub n is f, the nth derivative at c, all divided by n factorial. And if we were to expand this, this would be the 0th derivative. So that's just the function itself. So this is the function itself evaluated at c divided by 0 factorial, which we know is 1, plus f prime of c times x minus c. So that 1 factorial, also just 1, plus f double prime of c over 2 factorial times x minus c squared, plus f triple prime of c over 3 factorial times x minus c cubed, and so on and so forth forever. Okay, so this is Taylor's theorem. And it gives me a way to find the coefficients for the power series that represents a given function. So now the question is, where did this theorem come from? How did we find that a sub n? So we're going to now derive this formula. Okay, so let's try to understand what we are actually looking for. So derivation of a sub n, our derivation of a sub n. So we have f of x is equal to some power series, n is equal to 0 to infinity a sub n times x minus c, which if we expand to the power of n, that gives us a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared plus a sub 3 times x minus c cubed, and so on and so forth forever. Now, let's say that I want to evaluate this function at c. What does f of c equal? So f of c would be the sum n equals 0 to infinity a sub n times c minus c to the n. Now remember, we made the assumption, we said we're going to go with the convention that x minus c to the power of 0 always equals to 1, even when x equals to c. So if I were to expand this thing, that's going to give me a sub 0 plus 0 plus 0 plus 0 plus 0 forever. So this is just remembering x minus c to the 0 equals to 1, even if x equals to c. So what we got here then is that f of c is equal to a sub 0. So we actually just found a value for a sub 0. So now what we're going to do is we're going to take the derivative of this thing. So this is actually really straightforward for taking the derivative because power series are like infinite polynomials and the derivative of polynomials are super straightforward. So if I were to look at f prime of x, I'm not going to write the sum notation this time. I'm just going to go straight forward and do the derivative. Well, a sub 0, that's my coefficient. That's a number, so its derivative is just 0. The derivative of x minus c, that's 1. So what we have left over is a sub 1 plus 2a sub 2 times x minus c plus 3a sub 3 times x minus c squared plus, if I were to do the next one that I didn't write down up there, 4a sub 4 times x minus c cubed plus, and so on and so forth forever. So now what happens if I look at f prime of c? Well, f prime of c will be equal to a1. Check it out, a1 plus every other thing right there is going to be going to 0. So that's plus 0, plus 0, plus 0, and so on and so forth forever. Okay, so actually now we just found a value for a1. So we can say then that f prime of c is equal to a1. Now let's take the second derivative. Okay, so if I do my second derivative, f double prime of x, well, the derivative of that a1 is 0. And so now the derivative of the second part, 2a2 times x minus c, is just going to be 2a2 plus, then I'm bringing the 2 down, so I'll have 3 times 2 times a sub 3 times x minus c plus 4 times 3 times a sub 4 times x minus c squared plus, and so on and so forth forever. So notice I didn't multiply the 3 and 2 together to get 6. I didn't multiply the 4 and 3 together to get 12. And that right there is because we're trying to find a pattern. And as we'll see later when we actually do problems, when we're trying to find a pattern, it's good to have things in their expanded form and not all multiplied out. It will be easier to recognize what that pattern is. So right now, since we're trying to find a pattern, we're like, what is a sub n? So we're not going to actually multiply these things out. Okay, so now let's look at f double prime evaluated at the center. Well, that's just going to give me 2a sub 2 plus 0 plus 0, and then there'll be another 0 and so on and so forth forever. So this gives me that f double prime of c is equal to 2a sub 2. In other words, f double prime of c over 2 is equal to a sub 2. So now I just found my a sub 2. Let's do this one more time, and then we're going to see that there's actually a nice pattern that will have developed here. So let's take the third derivative. Okay, so the third derivative, f triple prime of x, will give me, first it'll have a 0, so then it'll give me 3 times 2 times a3 plus 4 times 3 times 2 times a4 times x minus c. If I were to have the next one there, it would be plus 5 times 4 times 3 times a sub 5 times x minus c squared. If I had started writing that one from the beginning, this would be really straightforward to see. If you want to go back and do that, you can. Plus, and then so on and so forth. So now if I evaluate this at the center, the third derivative will give me 3 times 2 times a sub 3 plus 0, plus 0, plus 0, plus 0, and so on and so forth forever. Which means that the third derivative evaluated at c is 3 times 2 times a sub 3. In other words, the third derivative at c divided by 3 times 2 is equal to a sub 3. And now I have a value for a sub 3. Well, if we think about what would happen if we take the fourth derivative, what we're going to have left is that 4 times 3 times 2. So like this is what would be left if I were to take the fourth derivative. Everything else would become 0. So I can actually see then that the fourth derivative evaluated at c divided by 4 times 3 times 2 is equal to a sub 4. And if we keep this pattern going, we could then surmise or see if we actually did it, that the fifth derivative evaluated at c divided by 5 times 4 times 3 times 2 is equal to a sub 5. Well, notice what's happening here. In the denominator, in the denominator, when I have that fifth one, I have 5 times 4 times 3 times 2. Well, times 1 doesn't change anything. 4 times 3 times 2, again times 1, 3 times 2. If we go back to the second one, that 2 is also just 2 times 1. If I go back to the first one, well, there is nothing down there. So that's like having a 1 down there. So what we can see is each time when I take the derivative, I'm multiplying the next number down. And so what I'll end up with is in factorial. So if I wanted then the nth a sub n, or the nth derivative evaluated at c, what I can see is that the nth derivative at c would be n factorial times a sub n. In other words, a sub n would equal fn c divided by n factorial. So I'm just going to go back and rewrite each of these. A sub 5, that's the fifth derivative at c, divided by 5 factorial. Hey, look, the fourth derivative at c, divided by 4 factorial. The third derivative at c, divided by 3 factorial. So we see that this pattern developed that allowed us to find these a sub n. So let's go back to the theorem and notice, hey, look, that's the same a sub n that we had in the theorem. And we were able to derive it ourselves just by taking derivatives over and over and over again. So this theorem right here is really important. It gives us a way to write a function as a power series, if that function has a power series representation. So when we do that, that series is called a Taylor series. So definition, a series of this type being f of x is equal to the sum n equals 0 to infinity, the nth derivative at c divided by n factorial times x minus c to the n is called, a Taylor series. And if I were to change this so that the center of this series is 0, well, that's going to make things easier because I'm plugging in 0 to find that derivative. That's what's called a Maclaurin series. So Maclaurin series is a Taylor series that is centered at 0. Okay, so we have one more definition before we finish this, and that's of something called a Taylor polynomial. A Taylor polynomial is like the partial sums of a Taylor series. If I were to look at just, for example, the n equals 0 to 3, well, that's getting me up to x minus 3 cubed. So that would be a third degree Taylor polynomial. So an nth degree Taylor polynomial is the nth partial sum of the Taylor series? In other words, it is some polynomial that represents a function, but where we're only looking at part of it. Okay, so that's all for this video. I'm going to make another video where we go through a couple examples. So I'll probably do a couple videos for a few examples so that we can see this in action, actually doing this and finding Taylor series and Maclaurin series for given functions. And then we're going to see how we can make this a little bit easier by using series that we already know. That's all for now. Bye, guys.